Hello and welcome to this video about circuits. We're going to look today at series circuits and parallel circuits. What do those mean and what are the implications for those different kinds of circuits? We're going to look at some household circuits and applications of series and parallel circuits to those situations. Electrical power, what does that mean? We talked about power, now what's electrical power? And we're going to look at energy usage and costs. So most electrical circuits are not this simple. It would be nice if they were, but they're not. This circuit has one power source. It has one device, the little light bulb, and it has one path for the current. Most electric circuits have multiple power sources, multiple devices, and multiple paths for current. We're going to look at two different types of circuits, circuits in series and circuits in parallel. And you can see from the diagrams that a circuit that is in series is where the circuit is wired from one after another. The parts are wired one right after another. Here's our power source. This is just a group of batteries that are providing the potential difference, the voltage difference. And in this series circuit, the current will be the same throughout the circuit. When any part of this circuit is disconnected, there is no current through the entire circuit. A parallel circuit, on the other hand, here we have our voltage difference, and in this case, you can see that there are two or more branches for the current. The voltage difference will be the same in each of the branches, but the current will be greater through the branches with lower resistance because we can have different resistance in each of these places in the parallel circuit. When one branch is disconnected in this situation, the current will continue through the other branches. So if we take this component out, current will still continue to flow through these other branches or the other components. So let's look at an example. When you take a typical graphing calculator out, requires 4 AAA batteries, most of them. If you take one of those batteries out from the calculator and then try and turn it on, it will not turn on. Why is that? Well, let's look at our two different types of circuits and think about what type of circuit must be employed by this graphing calculator. Do you think it is a series circuit or a parallel circuit? If you said it was a series circuit, you were right, because remember, when we remove any part of the series circuit components, it will not function. And that is because the current will not flow. So let's take a look at just a little definition here. When any part of a series circuit is disconnected, that circuit then is called an open circuit. When the circuit is open, it means it has been broken, or the current is not flowing through that anymore. So that is what that term means. Let's look at another example. In your home, when you turn off a light, does that make your refrigerator stop running? Well, not usually, at least for most of us. What type of circuit is employed in your home then? Let's look at our examples. It's just another way to draw circuits. This is the circuit in series and the circuit in parallel. These stand for the different resistors. And remember, in circuits in parallel, we can remove one of the components, or we can stop the current from flowing through one of these, and it does not affect the other ones. So most homes are wired with circuits in parallel. I thought this kitchen was pretty astounding with this bright pink. Most of you already know that in our homes in the United States, we are provided with 120 volts in our outlets for our potential difference, or you might, as it might sometimes be called, or voltage difference or energy potential. We usually have 120 volts at those different outlets. Some branches of the electric circuits will also wire for 240 volts. A lot of times your clothes dryers will run on that. Sometimes the stoves also will run on a 240 volts. Parallel circuits branch out basically from the circuit breaker, sometimes that's called the main switch or the fuse box, and go throughout our home in parallel. That gives us the ability to use some parts of the circuit without interfering with other parts. So it's important to mention that homes are usually equipped with certain kinds of safety devices in the circuits, because with current running through the wires, an increase in current will also cause an increase in heat in the wires and obviously a fire danger. So there are two safety devices that are typically installed in all households in the circuits. Fuses are one, and this is just a little picture of a fuse, what one might look like. If the current is too high, there is a little tiny piece of metal in the fuse which melts with current, really high current, or dangerously high current at some level. The circuit is then broken and no current can flow. So until that fuse is replaced, you will not be able to get current flowing through that particular part of the circuit, and you cannot use your outlet. Circuit breakers are another safety device. They automatically flip a switch when the current is too high, and that switch breaks the circuit so that no current flows and you don't get any electricity to that part of the circuit. And in this case, as many of you know, you simply have to go and find the main circuit breaker here and just flip whatever switch it was that was flipped off and flip it back on. And you can then close the circuit so it's no longer an open circuit, and you can get current flowing again and you can use your electricity. So that brings us to the idea of electrical power, which we hear a lot about. What is electrical power? It is the rate at which electrical energy is converted to another form of energy. So remember, power has to do with energy per time. As we learned before, power equals energy per time. When we talk about electrical power, we also use watts, just like we use watts with mechanical power that we've calculated before. But electrical power is going to be equal to the current in amperes times the voltage difference in volts. And that will give us our power in watts. A lot of times, when you're looking at electrical power, they will talk about kilowatts. And watts we abbreviate with a capital W. Kilowatts would be a lowercase k and a capital W. And 1 kilowatt is equal to 1,000 watts. It's an SI unit, so that should make it pretty easy. Let's look at an example using our formula for power, for electrical power. If the current in your clothes dryer is 15 amperes, when it is plugged into a 240 volt outlet, what is the power of the clothes dryer? Well, let's write down our formula and we can plug in values that we know. We know that power equals current times voltage. We know that 15 amperes is our current. We know that we have a 240 volt outlet. So we can then calculate what the power of the clothes dryer is. The power is 3,600 watts. Let's say we wanted to transfer this into kilowatts. A lot of times we refer to power in kilowatts. That would simply be 3.6 kilowatts, since there are 1,000 watts in a kilowatt. So now that we know how to calculate power, we can talk about the amount of energy that we convert from electrical energy into other forms, mechanical energy or thermal energy, in our various devices that we use. And we can do that by looking at this equation. The electrical energy, now this is going to be a little bit strange. The units in this whole equation are a little bit different. We're not going to use all SI units. We're going to say the electrical energy in kilowatt hours okay, not watt hours, but kilowatt hours, is going to be equal to the electrical power in kilowatts, and that should be a lowercase k, but we're going to use kilowatts instead of watts in this equation, in this formula only. And we're going to multiply by time, and in this equation only, time is going to be in hours, not in seconds. And that gives us our kilowatt hours. And we abbreviate that little k, capital W, and then little h for hours. So these are very different units than we normally use, but you have to keep in mind which units that we need to use for this equation. We can simplify it by saying the electrical energy, capital E, equals power, capital P for the electrical power, times the time, lowercase t. So let's try to apply this to a real life situation. Now I have a little like an electric kettle that I plug in to boil water, and oftentimes kettles have a power rating of 2.5 kilowatts. I don't know the power rating on mine. However, I did do a little test to see how long it would take to boil enough water to make 2 cups of tea in the kettle. And it took me 1.2 minutes. So how much electrical energy am I converting into that thermal energy? Let's use our formula and try and figure that out. We know that energy equals power times time. My kettle has a power rating of 2.5 kilowatts. And my time, the time that it takes to do this task, is 1.2 minutes. Now remember, I need to have time in this equation in hours. So you can either convert it all in one shot here, or you can convert it separately. If I convert it separately, I know that 1.2 minutes multiplied by my conversion factor, there are 60 minutes in 1 hour. Therefore, 1.2 divided by 60 equals 0.02 hours. You can see that minutes cancel, and I'm left with only hours for my unit. So I can plug this value into my equation for time, 0.02 hours. This is going to give me units of kilowatt hours when I multiply that together. My answer is 0.05 kilowatt hours. So you can try a few of these. Here's some more examples for you. Watch TV for an evening. How many kilowatt hours of energy are you consuming there, or transferring from electrical energy into your television set? And heating up an evening meal. Let's say it takes you 3 minutes to heat your meal up. How many kilowatt hours of energy are you using? Or playing a computer game for an hour. How many kilowatt hours of energy are you using? Keep in mind that you need to have your power rating in kilowatts. We had kilowatts for our tea kettle, but the television is listed in watts, so you'll definitely want to convert that. Also, make sure that your time is in hours, not minutes or some other measurement for time. Pause the video, try these, and then you can start the video again, and I'll have all the answers on the next frame. Here are the answers. Hopefully you got pretty close to what I put down here for the amount of energy that each of these activities uses, electrical energy. And you can pause the video and take a look and check your answers. So what is the cost in dollars to use this energy? Let's look at a situation where we have a light bulb burning. Let's say we have a 100-watt light bulb and we leave it on for 5 hours. How much electrical energy are we using? And from there, how much is it actually costing us? When we look at our formula for energy, remember electrical energy equals power times time. We know our power, we have that in kilowatts right here. And we know the time in hours already. So we know that the energy usage for running this 100-watt light bulb for 5 hours is 0.5 kilowatt hours. Now, we do need another piece of information. We need to know what the power company charges. And let's just suppose that the power company charges 15 cents per kilowatt hour. What's the cost of using that bulb? Well, the cost would be the kilowatt hours that have been provided or used, and then we multiply that by the cost per kilowatt hour. And if that's hard for you to come up with mathematically, if you write it out and you simply say the kilowatt hours of energy that we used, and we multiply it by the conversion unit, which is for each single kilowatt hour, the company is charging this much money. If we multiply those together, the kilowatt hours cancel out, and we are left with only the amount of money that we're being charged. So here we have our energy, the kilowatt hours that we used, 0.5 kilowatt hours. Multiply that by 15 cents per kilowatt hour, and we get 8 cents that we just spent to run that light bulb for 5 hours. And just to give you a little idea about how much energy different appliances use, and of course this varies a great deal on the type of the brand of appliance, how old the appliance is. If it's an appliance that's trying to save energy and use less energy when it's running, it has a lot of variables. But on average, these are the kinds of energy uses that you see in different appliances, from electric blankets to television sets to your freezer to even if somebody's got a pool pump or a spa, things like that. Obviously, washing machines and refrigerators use quite a bit. So that's just for your information to give you some ideas of that. Review. Make sure you know what circuits in series and circuits in parallel are, how they're alike, how they're different. Know different examples of where these kinds of circuits are applied. Know about how a circuit breaker works, what that function is, and fuses. Know how to calculate electrical power, how to calculate the energy that an electrical appliance uses, and how you would calculate the cost of using a particular electrical appliance. Here's some advanced ideas. You are welcome to answer these or come up with your own questions and your own ideas for investigation. So I look forward to what you have to show me, and I'll see you in class.